Good morning. My name is Justin Sears, Product Marketing Manager at Hortonworks. It's my pleasure to host our 7-webinar series entitled Discover HDP 2.1, covering all the new capabilities for Enterprise Hadoop delivered in Hortonworks Data Platform version 2.1. Today's Apache Storm for Stream Data Processing in Hadoop is the 6th webinar in the series. If you missed any of the previous 5 webinars, you can find those recordings, slide decks, and Q&As on our blog. Search for Discover HDP 2.1. I'll be your host today, and I'm joined by 2 Apache Storm experts. Himanshu Bari is a Senior Product Manager at Hortonworks. He is responsible for Apache Storm and Apache Falcon in Hortonworks Data Platform. Taylor Goetz is a Hortonworks engineer and committer and PMC for Apache Storm. Taylor has deep experience in master data management and holds 2 patents in the field. Here's today's agenda. We'll begin with key requirements for a streaming solution and an overview of some common use cases. We'll show an overview of Apache Storm, and we'll finish with time for Q&A. We've got 30 minutes, so we're going to move quickly. All attendee phone lines have been muted. If you have questions during the presentation, please send them to Himanshu Bari in WebEx chat. We will take time to answer those at the end of the call. If we do not have time to answer all of the questions, we will include a full Q&A in an upcoming blog post about this call. Let me set the stage for Himanshu and Taylor. This is a modern data architecture to store and process data from a wide variety of sources. Data comes in structured columnar formats and also newer, less structured formats, like those found in human-generated content such as Word documents or videos, in weblogs and clickstreams, in social content like tweets, and in machine, sensor, and geolocation data. Apache Hadoop works well in combination with familiar data repositories like RDBMS, EDW, and MPP to store and process a full spectrum of data. That data is then available to a variety of data access applications and BI tools to complete many different data workloads: batch processing, interactive query, stream analysis, NoSQL, search, and others. Through our experience with more than 200 enterprise customers running HDP, we know that enterprises need data management and data access as well as 3 additional capabilities. They need data governance and integration. Back to the original slide. They need data governance and integration. They need to secure their Hadoop cluster, and they need tools to manage cluster operations. In today's webinar, we will focus on one application for data access in Hadoop, Apache Storm for Stream Data Processing. We will cover Apache Ambari for cluster operations in the last Discover HDP 2.1 webinar next week, and you can look up details on the 5 previous webinars on our blog. Just search for Discover HDP 2.1. Now I'll turn it over to Himanshu Bari. He will start with key requirements for a streaming solution and then talk through some common Storm use cases. Then Taylor will give an overview of Apache Storm. Please remember to send your questions to Himanshu in chat. Take it away, Himanshu.
With that, the first question, why even bother with stream processing? And I like to look at this question in terms of two sections. First is, let's try and figure out what is the problem that it's trying to solve. And second is, is this the right time to solve it? So in terms of the problem, what we saw is as we were working with our customers through their Hadoop journey, and as they were trying to stand up Hadoop clusters, they started with the Hadoop journey with a simple goal that they wanted to be able to capture all the data that they were processing in their infrastructure, and then they wanted to be able to analyze that data in different ways. And as they went about doing that, and they got insight from the data, they came back to us and said, "Gosh, I wish I knew about these insights before and while the data was being generated, rather than after the fact." So they wanted to be more proactive about analyzing the data as it was being generated based upon what they knew from all the analysis in batch and interactive way that they were running on the Hadoop clusters. So that was the main need. Then the main drivers for that was if they are proactive, they can really drive a lot of efficiencies in their operations, or perhaps even find new business opportunities based on this data that was being generated in real time. And that was the main driver behind us going after the stream processing. So once we had that problem nailed, the second question becomes, is this the right time to really solve this problem? And the timing issue in my head is there's 2 aspects to that. One is economical and the second is technical. from an economic standpoint, processing real-time data is not a new problem. It's been done in the past. There are complex event processing or CEP solutions that do it, but they are extremely expensive. And because of that, what we saw is that many of the real-time stream processing use cases were being blocked out. They were just not economical enough for folks to actually adopt those solutions. And not only that, the second aspect, now getting into the technical things, were the CEP solutions would not scale for the new sets of data that was being generated in extremely high volume and at a very high pace. The traditional CEP solution just wouldn't scale to catch up with that. So you needed something new, some new solutions to solve that problem. And as we were doing it in conjunction with the Hadoop clusters, with Hadoop 2.x and the advent of Yarn, we saw a huge opportunity of bringing stream processing within the Hadoop ecosystem and run it natively on top of Yarn, right? So the problem was there, the timing was right, and that's how we decided to get onto the stream processing initiative within Hortonworks, and we really picked Storm. And I'll then now talk about why we really picked Storm. And there's 5 main reasons to that. First is it's highly scalable. So going back to the problem, the CEP solutions were there, but they wouldn't scale to the requirements of the newly generated real-time data. So Storm is an extremely scalable solution. So you can horizontally scale it like Hadoop. You can add and remove nodes as you need. And you do that economically because you're doing that on commodity hardware. And when you do that, something like that on commodity hardware, you want that system to be fault tolerant, and which Storm is. Storm is extremely fault tolerant. If a node goes down, it automatically reallocates the tasks running on that node to other running nodes. But as you achieve scale and fault tolerance, you still need some processing guarantees. And one thing to keep in mind is that many streaming solutions force use cases on either at least once or exactly once, and they're not flexible enough in terms of the processing guarantees that they can provide. But Storm does not have that limitation. It actually allows you to have at least once as well as exactly once processing semantics based upon the use cases that you have. Then, being a new solution, it's very important for a new streaming solution like Storm to have the right developer community to create the applications on top of Storm. The language agnostic feature that Storm has, where you can write your topology in Java or Python or other languages, is very helpful for that. So you can use the existing skill sets of your existing developers to develop topologies in Storm. And last but not the least is, it's an open source Apache project, and it brings all the brand governance and the large active community by way of Apache to the Storm project. Next, let's talk about what, now that we know that streaming is important and, Apache Storm is the solution that we went after, at a very high level, how do we see streaming fit within a Hadoop cluster or the existing data processing architecture that you might have? So, at a very high level, you will have real-time data that lands into your stream processing solution. The stream processing solution is going to do a number of things, ranging from simple data aggregations, filtering, to doing statistical analysis or machine learning algorithms to find out those insights and those anomalies that you're looking for in the data. And then it's going to persist those insights and anomalies, the thresholds, whatever you've computed, along with all the data that it's consuming, typically in a Hadoop cluster. That's by far the most common persistence layer that we see with Storm. Or you would also want to persist part of that data into perhaps your relational databases, because you have operational dashboards powered off of those relational databases. Your stream solution can also send alerts directly to your operational dashboards by way of sending information to messaging infrastructure or just persisting them into a relational database. The next part of this architecture is that now that you have all the data, perhaps in your Hadoop clusters, you still want to be able to run your analysis in a batch or interactive fashion. So those processes still continue to run. So you will keep on updating your view of the data in terms of going as far back in history as you can in your Hadoop cluster, and those batch feeds will continue to run and generate insights for you. And then as you do that, two things happen. One is, perhaps you're sending some of that information again to your operational dashboards, But the other more important one is you're actually updating your stream processing solution with the new insights that you get garnered now based on your entire historical view. So if you have certain thresholds or certain patterns that you're looking for, you update your stream processing solution with the updated information. So the next time, and from that point onwards, as it looks at data, it can react based on the updated insights that you've garnered from your Hadoop cluster. So that at a very high level is how we see a stream processing solution fit within your existing architecture. So, often people ask who's using Storm today, and there's a whole lot of different companies, small and big, who are using Storm. I've just got some of these logos from the Storm project website. If you are interested in knowing the exact use cases, please check out the Storm project website. It has information on what these companies are exactly doing. But one interesting thing you would notice is that, if you were to try and classify these different startups into, individual industry verticals, you would see that it has great adoption across a whole bunch of industry verticals. And what that means is that it's not limited to a certain set of use cases. It's very flexible, and depending upon what vertical and what use case you have, you might want to explore Storm for those use cases. So as we work with customers, we wanted to try and look at what is the most broad pattern that we see in terms of what people are trying to accomplish with Storm. And what we see is that, at the end of the day, when you stand up a Storm cluster and put a topology in production, you're really trying to do two simple things. Either you're trying to prevent something from happening, or you're trying to optimize certain aspects. And as you go, and as we went through the different verticals and tried to classify the use cases into these two buckets, we saw them really very well fit into these buckets. From finance to manufacturing to transportation to web. I'll give an example. We have a large tech company on the West Coast, and they had a use case around being able to look at network packet data in real time to prevent intrusions or to prevent certain fraud from happening within the network. So they have a Storm cluster where they're ingesting this data side by side from the switches. They're doing some simple filtering on this data, and then they're persisting that data to a NoSQL store as well as to their Hadoop clusters. But my point here is that the use cases are really broad, and they at the high level they fit into these two buckets of either preventing something from happening or optimizing certain aspects of your infrastructure. Okay, so one key benefit as we work with customers in implementing Storm that we see is its extreme flexibility. Now, when you look at a stream processing solution, there are various aspects that go along with that solution. First is where are you going to consume the data into that stream processing solution from? So Storm is flexible. It allows you to consume data from messaging infrastructure that are based on JMS. Many customers have existing investments in JMS and existing JMS infrastructure, so you can plug Storm into those JMS-based messaging systems and ingest data from JMS into Storm and then process it. Or you can use a messaging platform like Kafka, which we see a lot amongst our customer base. Then the second aspect is, since Storm doesn't have any data persistence layer built in, where do you store this data? So Storm can store data into HDFS, and that's by far the most common destination we see, where regardless of what you do with the data, all the data that's flowing through Storm ends up within your Hadoop cluster on HDFS. And then you can also save certain parts of that data or the results that you are computing on the fly into a relational database. So you have any relational database, so you can have your operational dashboards get updated based on that. Then the other part is in-memory caching platforms. Now again, Storm is flexible where it can work with in-memory caching platforms like Redis or Memcached. And the typical use case there being that you need certain reference data that you want to hold in memory, and that should be accessible to the entire cluster. So you want an external caching platform that you can talk to from your Storm topology. So again, Storm is quite flexible there. You can develop connectors to any memory caching platform that you want. And then there is the NoSQL databases. So typically we see HBase as a destination. Cassandra also comes up a lot. But it has connectors. Storm has connectors to both of these databases. You can store data there. or you can have search platforms consume data off of Storm, so you can have your analysts run search queries based on results or all the data that is coming off of your Storm topology. And then on the top, you have application development platform. So based upon the language that you choose to develop your topology on, you can use the IDE of your choice to develop Storm topologies. Okay, so this is a good segue for me to hand it over to Taylor, who is now going to cover the details of what a Storm cluster looks like, what are the different concepts. So Taylor, it's all yours.
Thank you, Himanshu. I'm going to start with a quick technical overview of Storm, and then I'd like to open it up to questions. If you have any questions, please enter them in the chat window addressed to Himanshu, and we will do our best to answer them during the Q&A session. If for some reason we don't get to all the questions, we will note them down and they will be answered in a follow-up blog post. So Storm's architecture. Storm consists of three main components. There's Nimbus, Zookeeper, and supervisors. Nimbus is similar to a master node in Hadoop. Nimbus handles code submissions and distribution throughout the cluster, and also assigns work to other machines in the cluster. In addition to that, Nimbus monitors the health of the cluster and can perform work reassignments in the event of failure. Zookeeper is used to store cluster state, and communication between Nimbus and the supervisors occurs through Zookeeper. So it stores cluster state, worker and task assignments, and also handles heartbeats between the worker nodes and Nimbus itself. And supervisor nodes manage one or more workers, for example, launching them and restarting them if they exit abnormally. Now, what supervisors are responsible for doing is launching workers that actually do the work of your streaming computation. In that sense, workers are just JVM processes with multiple threads that run the different components of your computation. So let's take a look at Storm from a conceptual standpoint. Conceptually, Storm computations consist of tuples, streams, spouts, and bolts that form a network called a topology. The tuple is the primary data structure in Storm, and a tuple is essentially an immutable set of key value pairs. And values can be primitives or serialized objects. And multiple tuples form a stream. And a stream is essentially an unbounded sequence of tuples. Within a topology, you have spouts. Spouts emit a stream of tuples. They're basically a wrapper around some streaming data source. So an example of a streaming data source could be a Kafka queue, a JMS topic or queue, the Twitter fire hose, what have you. So let's look at an example of a Storm topology. This diagram illustrates a single topology that counts hashtags in real time from a Twitter feed. On the left, you have a spout that reads tweet data and emits tuples containing the tweet and the associated metadata. The tuples from the spout are then routed in a round-robin fashion to a bolt that normalizes the data and emits cleaned-up data as a stream of new tuples. Those tuples are then routed and grouped in such a manner that the same hashtag, tweet with the same hashtag, are always routed to the same bolt instance. And that keeps a running count of each hashtag. And the reason why it sends the same hashtag to the same bolt instance is because those bolts can be parallelized, meaning they're running on multiple machines in the cluster. And finally, the counter bolt emits the running counts to a bolt that updates a live report. So what is Trident? Trident is a high-level abstraction that's built on top of Storm's core primitives. It's part of Storm. Trident is just the name of the API and the associated functionality. Trident provides an alternative method for defining topologies where tuples are processed in small microbatches. That's as opposed to one at a time, which Core Storm does. And this batching mechanism basically allows you to achieve exactly once semantics within Storm. A good analogy of that is that Trident does with Storm's core primitives what something like cascading or PIG does for MapReduce. So with Trident, the core data structure is still the tuple, and you still have spouts. But instead of writing bolts, you define filters, functions, aggregations, and persistent states for processing tuples. Trident comes with many of these predefined, but you can also write your own. Trident also batches tuples, and batches of tuples are assigned a unique ID, and that unique ID allows operations to be performed transactionally. That forms the basis of Storm's exactly once processing guarantee. Trident batches can also be partitioned into smaller segments so they can be processed in parallel across multiple machines. So Apache Storm is now integrated with Apache Ambari. So it's possible to install and monitor Storm with Ambari, which is nice. It gives you valuable metrics about the performance of your Storm cluster, and also allows you to expand that cluster in addition to other Hadoop ecosystem components. And with that, I think we're ready for some Q&A.
Question. So, Himanshu, go ahead. Have you gotten any questions we can take?
Yes. So the first question I have is, what is the difference between HBase and Storm, and what scenarios can suffice for HBase versus where does Storm become a necessity? So let me take a crack at it, and Taylor, you can perhaps refine and add more color as you see.
Okay.
So basically, HBase and Storm were created to address separate problems, right? HBase is your NoSQL store. If you need very low latency reads and random writes at a scale, right, which you can do over HDFS. You would stand up an HBase cluster which stores data within HDFS at the end of the day, but provides you that interface to get those low latency reads. Now with Storm, but with HBase, right, as you load up your HBase clusters with data, you're still not processing them. You don't know what that data is until you actually land all the data into your HBase cluster and then run queries and then look at the data. So that's the main value addition of Storm, where you would typically front a Storm cluster in front of a HBase cluster. So as that data is being ingested on the fly, you run that data through Storm. Storm looks at the data, it does some computations, and typically what it would do is that it would persist your resultant data into your HBase cluster. So Taylor, you have anything else to add on that one?
No, just that alone, Storm does not perform any persistence out of the box. So, but what you do is you use bolts and Trident state implementations to write to a data store. So in that case, you would use an HBase Storm component that actually does the writing to a data store.
The next question is, can Storm and Hadoop coexist on the same cluster? So the answer to that is yes, absolutely. They can coexist in the same cluster. Today, you can install your Storm cluster on top of the same nodes or that perhaps might be running your Hadoop cluster, but it's not supported to be running as part of Yarn yet. That's something that we are working on, and it should be available soon. So soon, Storm will be a native application to Yarn, so you can natively run Storm as part of Yarn, as part of your Hadoop cluster. Okay, so the next question is, let's see, can Bolt replace the functionalities done using Pig or Hive? So I would say that the Bolt in Storm today is pretty open-ended. You can write your business logic as part of a Bolt, which gets plugged into your Storm topology. And there are initiatives in the community where Yahoo has already worked on creating something called as Pig on top of Storm. So you write your Pig scripts, and those spit out Storm topologies that are basically Trident topologies that provide you that exactly once processing semantics. So the next question is, if Storm and Flume are related, if not, what is the differentiator point? So we get this question a lot. The key thing to note here is, Flume was created to aggregate all this data as it was being generated across all of your multiple infrastructure over hundreds of servers, right? But you can't really do any sort of heavy processing on the data. If you have a machine learning algorithm that you want to score on the fly based on the data that's being generated in real time, you can't do that with Flume, right? So the whole point of Storm is that it allows you to do that processing on the data. You can perhaps take data from Flume, put it in a messaging infrastructure like Kafka, and then connect Storm to Kafka and then do the processing. So there's various ways of how you can interleave Flume and Storm together. Taylor, do you want to add anything on that question?
No, I think you covered it pretty well.
Cool. Let's see. So there's another question. Can you explain Trident a little bit more with a use case? So, I can take a crack at it, Taylor. But do you want to take this one?
Sure. So Trident's use cases are basically the same as Storm. Trident is just an API that's higher level than the Storm core API. The one thing that you can do with Trident that you'd have to do much more work with Storm's core primitives is exactly once semantics. So with core Storm, it's very easy to do at least once processing, but it requires a lot more work to do exactly once. And what Trident brings to the table is it brings you the ability to do that easily. And it supports transactions, so you can transactionally process data in small batches. And like I mentioned in the presentation, Trident is a micro-batching framework. So in that sense, it can support a little higher throughput at the sake of some additional latency overhead.
Yeah, I think that's it, Justin. What we can do is I will aggregate all these questions and we will put out a blog, guys, around answers to these questions, since we were not able to get all of these today.
Great. Himanshu, if you could advance the slide and then we'll wrap it up. Fantastic. Well, I want to thank Himanshu and Taylor for taking time to share your expertise around Storm and stream processing in Hadoop. And I also want to thank all of you attendees for taking time today to join us. If you haven't signed up for the final Discover HDP2.1 webinar, you can do that from hortonworks.com/webinars. And next Thursday's webinar is on June 26th at 10 a.m. Pacific time, and it will be on using Apache Ambari to manage Hadoop clusters. We hope you can join us for that next week. And this ends today's webinar. Thanks for joining.